In data science, we work with massive data sets and complex models. The problem? Every time something changes, we need to rerun everything from scratch, wasting more time and killing more trees with computation power. What if we didn't have to do that? I'm talking today about a game changer in data science, and it's called incremental computing. So I started my career as a quant, expecting to go into it using my probability theory and risk-neutral pricing methods, but I was in for a shock because the dream that I had of quant life was dead. Quants don't spend a lot of time making these fancy models anymore. In fact, they spend a lot of their time dealing with data. And a lot of it. I also started my career in a team with heavy oversight, which meant that we had huge testing requirements. We had to run over daily data, trades from equities, FX, interest rates, commodities. We had tens of different time series for oil alone, and that's before you even start looking into the individual stocks. Every single night we'd run the exact same process, the exact same calculation and almost the exact same trades with only one major difference: the extra day of data. But that's how data science works, right? When something changes in the underlying data, then we need to rerun everything from scratch. But what if it didn't have to be that way? Incremental computing is the idea that if things haven't changed, then we don't rerun them. It's a simple guiding principle. Humans can understand it pretty well. It makes a lot of sense. But as with a lot of things, translating that into something a computer can understand is a whole different kettle of fish. So let's start with a really simple example. Say you have all your data in one big table and you want to do a really basic data cleaning step, and that's replace all the nulls with 0. The easiest way you could do this is probably grab a pandas.fillna function and there you go, bash, one line of code, you're all done. Simple. The issue is when you do the same thing tomorrow, you're recalculating the same step on a load of the data already. Now, you could fix it in this simplified example by just doing fillna on the new row of data, but in the real world, the data cleaning step is a whole lot more complicated than this. Because in most cases, data processing isn't just done once. There's things that may be standard across loads of data, like filling nulls with 0, but there might be things that are specific to the model in that particular use case. For example, currency conversions in foreign exchange models. Often the process is so far abstracted from the business use case that there isn't really a concept of this is the last day of data anymore. But yes, in theory, if you took this use case by use case and set it up so only the most recent day of data is the stuff that's calculated, then yes, you're saving your computation time. But that only covers one scenario. Things like errors in the data that need the whole thing updating, or maybe new assets being added, require a recalculation of everything. Trying to capture all potential edge cases is an exercise in futility. What if we had something better? A way to track exactly what has changed and only rerun things according to that. That is the fundamental concept behind incremental computing. So we can frame this in terms of mathematics. We might have a function f which has parameters x1 to xn, which is our data. Now, say there's a change in our data. Let's say instead of xk, we have xk star, which equals xk plus some delta of xk. Traditional programming would have us rerun the entire function just because that one variable has changed. But incremental computing says something different. That says, let's calculate the differential df by dxk. Hey, Lee in the edit here. I'm homesick today, so sorry if I sound a bit rough, but what I wanted to do was actually clarify a few points here because I don't think I did a good job when I filmed this. When I talk about the differential coming up, I'm talking about literally the mathematical definition of differential, but incremental computing actually abstracts out a little bit wider than that to talk about recomputing the part that's changed only. So that doesn't necessarily mean you have to do the mathematical differentiation. We're going to dive into these topics in a little more detail in upcoming videos, but I just wanted to make that clear because I'm going to be talking about the mathematical differentiation for the next section, but I will link it up to how that links into general incremental computing at the end of the video. Which actually brings an interesting question to mind, because we know how to differentiate maths, but how on earth do you differentiate a programming function? The easiest way we can get some of the power of incremental computing is to do something called partial evaluations. And we talked about this earlier when we talked about using fillna. If we know we'd already calculated on all the previous days, then we can only calculate the latest day, which is the data that has actually changed. If you've ever written something in your code like full sum plus equals sum, then you've already done a little bit of incremental computing. But much like differentiation is easy when we're using simple functions like x plus y, the real world is where the maths gets a little bit more complicated. When you were taught differentiation at school, you probably started with something really simple like fx equals x squared plus 2x plus 1. And you probably taught it like this, like you bring that power down, so that becomes 2x, and you decrease the power, so 1, you don't even write 1 there, This case, you go x to the power of 0 is 1, so it's 2x plus 2, and you zero out the constants. So you get df by dx equals 2x plus 2. And you were taught this formula for how to do it. But the maths gets a little bit complicated. I mean, when you learned fx equals log x, you couldn't just follow some formula to differentiate this. You had to explicitly learn that df by dx equals 1 over x. When it comes to data science, our functions are typically pretty complex and involve multiplying or dividing many rows or columns, maybe taking exponents or using functions that have no kind of obvious way to differentiate them. So they fall under the category of not easy to differentiate. Instead, we need a way to do this programmatically. Enter adjoint automatic differentiation. AAD. Do you remember the chain rule of differentiation? For those of you who need a quick refresher, it's the idea that if we have a function y equals f of g of x, then dy by dx is df by dg dotted with dg by dx. A programming function is, at its most basic level, a function of functions. So if we can differentiate all of its component parts, then we can differentiate the entire function using the chain rule. Automatic differentiation can be done in one of two ways. Bottom up, known as the tangent method, or top down, known as the adjoint method. We start with the function we have, the top level, and then move down through all of its functions inside it, differentiating them all in the same way. This is the computer programming technique of recursion. The main reason that this is used is because it's generally far more computationally efficient than the tangent method, particularly in the case of programming where we have more inputs than we do outputs. This is because we only need one sweep of the dependency graph to be able to calculate outputs per all inputs. However, it does have greater demands in the form of storage, keeping track of each intermediate step and the instructions that produce them. Now, there are ways to make this more efficient, but actually this is very useful in incremental computing because all of these stages saved to the tape of operations, as it's called, are partial evaluations. This means that we can reuse previous results instead of having to recalculate them. So in a world in which we have full AAD on our code base, then incremental computing comes for free. Easy, right? Except the devil is in the detail, as usual. The implementation can be really complex through things like nested function calls, loops, all sorts of computationally challenging things that we take for granted in the world of programming. Calculating the exact way to propagate derivatives through all operations is not an easy task by any stretch of the imagination. As we mentioned earlier, differentiation is not always straightforward either. Conditional statements, indexing, external library calls, all of these can scupper even the most well-implemented AAD attempts. There's also the question of memory. The more complicated the program, the bigger the tape of operations and the more stuff that needs to be stored. So incremental computing sounds amazing in theory. How do we actually use it in practice? Now, I'm talking about this today because I have a little something up my sleeve. At EvilWorks, we have created something for data scientists that is fully AAD implemented, so there's no more waiting around for massive chunks of code to rerun. You can only run the bits that actually matter, and we've taken care of all of those tricky details so that you don't have to worry about them. We've also added many features that should just be standard in data science. Want to add feet to meters? No worries, we've got you covered. The conversion will happen under the hood and you can have it in either output you want. How about adding feet to Celsius? Well, we're going to error you out because that's a little bit weird and we don't want you doing that. What about adding GBP to EUR? Again, we're not going to let you do that unless you knowingly override it, and in which case, that one's on you. You can't blame us for not warning you. These features and more are all part of our toolkit, and we are having a closed beta in February, so you can try this out for yourself. To see the full list of features and find out how you can be a part of it, look at the details linked below. In the meantime, let us know any questions that you have about this or data science in general. Like and subscribe, and we look forward to seeing you in the next one.